So I updated the website. The chapter 15 problems are due on Monday because we're going to finish up chapter 15 today. So that's plus 2 lecture periods. I'll give you back your exams. I'll scan in the answer key if you have any questions about those. I put the scores in, but they're muted, so I have to unmute them, and then it'll update your percentages and everything. Remember, this is just the first of 4 exams. So if you want to come and talk to me, feel free, and we can go over it. And then we're going to start into chapter whatever it is after we skip through the spectroscopy chapters. Okay. So do you have any questions on? I have one last thing to talk about in the ethers that'll help you do the top hat electronic problems. But do you have any questions on those? Okay, I'll take your homework problems then after when you're leaving. The last thing about ethers is the idea of how you do what's called a protection of an alcohol as what's called a Silyl ether. So let me give you the following problem. Let's say that I had this molecule with both the alcohol and the bromine functional groups. I would like to react this with magnesium metal, followed up then by reacting it with CO2. So my ultimate goal here is to make this molecule, is to make that carboxylic acid. And so hopefully you still remember that if I make a Grignard and react it with CO2, I'll get the carboxylic acid. So I try and react this bromine with the magnesium, and what happens? Well, will it make a Grignard? So if I try and react the magnesium bromide, I'm going to make that molecule. That's what I'm trying to make. Will it make it? No? Why not? What's that Grignard going to do to the alcohol? It's going to deprotonate it. Now here's the thing we have to think of, because we're so used to doing reactions on paper with a single molecule. In the reaction, there's billions of molecules, right? So what's going to happen is that once I make a Grignard out of this side of the molecule, it's going to react, if not with itself, and it's questionable whether it can stretch across there, but certainly it might react with another molecule, and it'll certainly deprotonate that alcohol, and then you're going to kill your Grignard. All right, so we're going to put an H there, and then we've deprotonated to make like an alkoxide. So we cannot make Grignards in the presence of any acidic hydrogens, like OH, carboxylic acids, and NHs. So when we start doing reactions with multiple functional groups in them, our problem is that sometimes we try and make one functional group in one part of the molecule, but it's not compatible with the other functional group. And this is the example of that. So I could not do this reaction unless I somehow make the OH group unreactive. And there's a number of ways to do that as ethers, but the one that Top Hat introduces is the idea of using what's called a Silyl ether. So a Silyl ether is one where I'm going to attach a silicon molecule to the oxygen. That's going to be a Silyl ether. And this is what synthetic chemists have to deal with all the time. They've got to convert one part of the molecule to keep it from reacting. But the whole idea here is if I convert this OH into something that will not react with the Grignard, I've got to get it back at the end. So for the Silyl ether, what you do is you can react an alcohol, in this case, this molecule with, we could react it with something like trimethylsilyl chloride. Now the silicon chloride bond is going to react like our sulfur chloride bond that we use for tosyl chloride. This is going to end up reacting with the OH, and I'm going to end up eliminating HCl. So I'm going to end up with my O attached to my silicon with my 3 methyl groups. And so I'm going to make what I would call a trimethylsilyl ether. And there's different alkyl groups you can have attached to the silicon. But this is just one of them. The reason I'm choosing trimethylsilyl is because if you remember back to spectroscopy, we used tetramethylsilane as our reference to be 0 parts per million in NMR. And so this is just a trimethylsilyl group. So once you convert this OH group to a silyl ether, it will not react with the Grignard. So now I could go ahead and I could react this alkyl bromide with the magnesium, and I don't have to worry about it deprotonating the OH. And so if I continued this sort of synthesis, what I would have is I would have my O with my silyl group, and then over here I would make my negative charge, my MgBr plus, and now I could go ahead and react this with carbon dioxide so that I could make the carboxylic acid and my silyl group, my silyl ether would stay intact. So the silyl ether doesn't react, this doesn't react with acid or base. It does not react with acid or base. So once I put the silyl group on the oxygen, it's stable. And so now I could complete my synthesis. I could make my carboxylic acid, and now I just have to turn my silyl ether back into an alcohol. So, and this is sometimes called protecting. The silyl ether could also be called a protecting group because it's protecting the OH group from reaction. So my initial problem was that I wanted to react this molecule with both the bromine and the OH in it with magnesium to make this Grignard, and then react that Grignard with CO2 to make that molecule. The problem was that once I make the C-, I can't have an OH present, and so it gets deprotonated and it kills my Grignard. So now what I've done is I've protected my OH group as a silyl ether so that now I can make the Grignard out of it and then do my reaction. And then I just need one more reagent to get rid of that silyl ether and turn it back into an OH. And what that reagent, the commonly used reagent is just fluoride. So if you use a fluoride ion, something like sodium fluoride or potassium fluoride, it will remove the silicon from the oxygen. Because the silicon-fluorine bond is one of the strongest bonds that there is. And so we'll immediately remove that silicon, and it will, what we then call, which I'll write, a deprotect. It deprotects the OH, or the silyl group. Okay? So I now take this molecule, I say let's add sodium fluoride to it, and I get back my OH. I still have my carboxylic acid that I just made, and then my trimethylsilyl now fluoride. And that is a very strong bond. So this would be what we would call the deprotection stage. So this is just one of the examples. I don't know if they talk about, I didn't get a chance to look in the chapter if they talk about things like mom groups or other things. But there's a half a dozen ways to convert OH groups into an ether that will not react. And the silyl is just the easiest one to use. So people that do synthetic chemistry, particularly people who do sugar chemistry, so if you think about the basic structure of a sugar, I'm just writing it out as in its flat cyclohexane form, not in the chair. But there was a stream of thought back in the 70s-ish, particularly when we had issues with the Arab oil embargo, so that there were gas lines and stuff like that. Could we make everything that we need from sugar instead of crude oil? And we still do that. They put sugar molecules onto drugs to make them easier to go into the cells and things. But if you're going to take a sugar and you're going to synthesize it, you have to somehow differentiate those 5 OH groups from each other so that you can get one to react, but not the other 4. And so there's a lot of protection of those groups, but then you've got to deprotect them in the end. And so we'll talk a little bit about that. We'll show some of those methods later on. So people who do sugar chemistry spend half their time protecting an OH and then unprotecting it, and then protecting another one and unprotecting that one. So they spend half their time doing nothing more than just protection, and the other half of the time they're actually doing something. But that's kind of how it has to work in order to protect those, in order to keep the molecule sort of reacting where you want it to. Again, this is the complexity we get to when we have molecules with more than one functional group. Okay. So that's the silyl ether part of chapter 15, and that's the last part that's left. Okay. All right. Okay. So if you came in late because of the snow, I'll put the video up, and this is just the end of chapter 15. It could have been not just snow. Right? So any questions? So that there's probably a couple problems in the in-chapter problems, and those are due Monday. So then we move on to chapter 16 and 17, I believe, are spectroscopy, or 16 spectroscopy. And then we go to free radical halogenation, that I won't say is normally done in the first semester, because that was a past and nobody knows that. Oops, I just said it. So now we'll talk about free radical halogenation. And the first part of chapter 17 is like bond energies and a lot of the nitty-gritty sort of reasons why free radical chemistry works the way it is. I'm going to skip right through that, and we're going to go to the reaction. And our reaction is called free radical halogenation. And it's got a number of facets to it. We're going to invoke Hammond's postulate from last semester at least once. So what is free radical halogenation? Free radical halogenation is when you take an alkane, and I'm going to make this a CH3 with the CH bond explicit, and we're going to react this with a halogen. Br2, this could be Br2, or most likely Cl2. Iodine doesn't react very quickly, so we don't normally do that. And fluorine, if you had fluorine gas, which is one of the most reactive substances, the fluorine gas will just explode when it hits an alkane. So we don't do any fluorination. Then it's basically fluorine, most reactive, then chlorine, then bromine, and then iodine. So really, these are the two that are the most useful. And what's going to happen is that we're going to do a substitution. So let me write this as XX. So Br, Cl, two halogens. And I'm going to do a double substitution here. Or I guess in general chemistry, what you would say is a double replacement. So I'm going to end up with the CH3 attached to the halogen, and then I'm going to end up with HX as the other product. So the whole idea here of free radical halogenation is to substitute a hydrogen with a halogen. And this reaction is incredibly important because there's only two things I can do with alkanes. Right? If I just have a normal alkane like methane, there's only two things I can do with it. I can react it with oxygen gas and do what kind of reaction?
Combustion.
I can do combustion with it and form CO2 and water. And it's not that that's not an important reaction. Right? I mean, that's how we keep the houses warm. If this alkane is octane, that's how we drive the cars. Right? The evil fossil fuels that apparently we're not going to have in 10 years. This is the current proposal in Washington. I don't know if I'm going to be here in 10 years or not to see that, but combustion. From a synthetic point, combustion is kind of like, wait, I'm just making CO2 and water out of it. So this is an important reaction, but it's not good synthetically. And synthetically, what I'd like to do is to take my unreactive alkane, like pentane, react it with bromine, and then put a bromine in the place of a hydrogen. Because what can I now do with that bromine? What can't I do with that bromine? How many reactions could I do with this molecule? A lot, right? I could do SN1, I could do SN2, I could do E1, I could do E2, I could turn it into a Grignard, and then react it with a carbonyl, or an epoxide, make it a double bond, turn the double bond into an epoxide. It all starts here with the bromide. Remember, alkanes, skeleton that I hang functional groups off of. So if I start with my skeleton, which is crude oil, it has some other mother's milk of organic chemistry. We'll talk about coal later. But all I have is a skeleton. I've got to take one of those hydrogens and I got to replace it with something that I can do something with. This is the key reaction. So anytime I want to make A into B and B into C and C into D, if A is an alkane, free radical halogenation is the first step. So that gives me a handle to work on with the molecule. Okay. So that's why this reaction is important. All right. Everybody kind of with me there? So you saw this in all the homework problems from last semester, and people would ask me, do we know this? No, we don't know this. We'll know this next semester. We're at next semester. So first of all, we got to talk about the mechanism, and then we have to talk about basically the selectivity, because I do have some control over where I put the halogen. And so this is the reaction I'm going to do, free radical halogenation. It's substitution reaction. Okay. So let's start with the basics. What's the mechanism? So let's take something like CH4. I'm going to take CH4, I'm going to react it with something like bromine, and my overall final product will be methyl bromide plus HBr. Now you might say, is it possible to add more than one bromine to the alkane? Yes. We're going to ignore that, and we're just going to add one halogen. But the reality is, if I took something like pentane and added bromine to it, I would end up with all the possible monobrominated products and some dibrominated products and probably some tribrominated products. It's been like 15 years since I've done that, but the last time I did it, I put it into the GC mass spectrometer. I ended up with all these peaks, and they were all the different bromides. So you could do that. We're just going to do monobromination. So this is a 6-step mechanism. And this would be the first mechanism that we learn if this was last semester, which I shouldn't be so fixated on, but I am. So what's the first step? The first step is called initiation. Whenever we end up with a free radical reaction, we always are going to have initiation, propagation, and termination steps. So we'll start with the first step, which is initiation. And what does initiation do? It starts the process. So I'm going to take my bromine, and I'm going to either use light or heat to break the bromine molecule apart. Since the two bromines have the same electronegativity, neither of them can take the electron from the other one. They got to split 50-50. And so now I'm going to use my fishhook arrows showing the movement of one electron to each one of those two bromines. And I'm going to make 2 Br dots. Now, if I put in all of the lone pairs around the bromine, I would end up with all the lone pairs around the bromine atoms. And that is a bromine atom. That's all that is. So I took molecular bromine and I broke it apart into its atoms. I may call those a radical, but technically they're just bromine atoms. And there's not going to be any charges in any of these steps, because I'm going to homolytically cleave every bond, which means every atom gets an electron. Okay. What did I leave the middle for? The transition state. So what's the transition state for this reaction? It's the Br ... Br. So it's breaking the bromine-bromine bond. No need for delta plus, no need for delta minus. There's no charges. So there's step one, initiation. So if I take my bromine, I add my bromine to my alkane, I'm going to shine light on it or I'm going to heat it up. And the first step is to break the bromines apart. And now I have my unpaired electron species that are going to do havoc to the rest of the reaction. So one initiation step. Then I'm going to do a couple of propagation steps. It can be really intense light. So if I was going to do this reaction, I could use ultraviolet light, but that would probably be overkill. I could put my bromine and pentane, and if there was sun, so I'll have to wait until like May in Cleveland, but I could put it in the sun and you would see the bromine, which is orange, that color disappear as the reaction occurred. In the days when we had overhead projectors, you could put on the overhead projector and the intensity of that light would cause it to go. So there's no requirement to be a really hard ultraviolet light. It can just be a really intense light. Olivia?
Is there a specific instance when you use light overheat?
We're going to talk about that on Friday, probably. Because that's going to lead us to the ability to select where we put the bromine. So light's normally going to be done at room temperature, and when we talk about heat, heat's going to be usually like greater than 300 degrees Celsius. But we'll get to that. Propagation. My Br dot now would like to abstract, is the term, the hydrogen from methane. And so what's going to happen is I'm going to break the CH bond homolytically, meaning that each atom gets an electron. My H dot is going to pair up with my Br dot, and then I'm going to form a C dot. So this is the way the arrows would look. I'll have a transition state, which I'll write in a moment. Then I'm going to have my Br attached to my hydrogen plus my CH3 dot. Okay. So I basically am breaking the CH bond, and the H dot is going to pair up with the Br dot. The C dot is now a radical because it's a carbon with an unpaired electron. The transition state is going to look like this. I'm forming a Br H bond. I am breaking an H C bond. And so my transition state will have dotted lines between the Br, the H, and the C. Again, no delta plus charges, no delta minus charges because there's no charges. We kind of have an advantage because we've written a number of transition states to this point, but this is the first transition state that we would have written like last year in a slightly different format. So there's one propagation step, and I'll get to why it's called propagation in a minute. Okay, I now have my CH3 dot, my very reactive radical. And what it does is it now reacts with a Br2, which means I now have to go back to the top and say, well, wait, did you break all of the bromine-bromine bonds in your initiation step? No. All I need is one bromine molecule to break apart, and I now form two bromine atoms. And so once I form a bromine atom, it comes down here, reacts with a methane, and I form a CH3 dot. My CH3 dot's going to react with my mostly intact bromine. And when it does that, the bromine's going to break apart into two Br dots. One of the Br dots is going to pair up with the CH3 dot, so that I have a CH3 attached to a bromine, and then a Br dot, a bromine atom. So the problem with bromine, well, the problem with any kind of unpaired electron or radical is the fact that usually when a radical reacts, it generates another radical. And so the process just spirals out of control. So all I need is one molecule of bromine to break apart for this entire reaction to basically like sustain itself. Because one bromine generates a new bromine. Hence the term propagation. One bromine propagates another one. So this process can get out of control very quickly. And when's it going to stop? Well, it's going to stop when you run out of stuff. Or it's going to stop when we do one of the three termination steps. Okay. So we're at 3 of the 6 steps. Initiation, the 2 propagations, and now we need to terminate the process. Oh, transition state. What's a transition state going to look like? You're going to have a CH3, a Br, and another Br. What am I doing? I'm forming the CH3-Br bond, breaking the Br-Br bond so that there is a transition state. So now let's terminate the process. And when we do a termination step, basically here's how we have to think of it. I'm going to bring 2 radicals, 2 unpaired electron species together. They're going to share their electrons, and I'm going to make a bond and stop the process. How many different radicals do I have? Technically, I have a Br dot and a CH3 dot. So that's like A and B. So how can I bring A and B together? 2 A's, 2 B's, an A and a B. So that's my final 3 steps. I could say for termination step number 1, 2 bromine atoms come together. They share their electron pairs. I go through the same transition state that I did in terms of breaking them apart, and I reform bromine. So that's one termination, 2 A's. Or a bromine could come together with a CH3 radical. Again, both sharing their unpaired electrons. Going through a transition state where I'm forming the CBr bond. And then I form a molecule of the product. So that's A and B. Now the new reaction, the new product, is going to be, what if two methyl radicals were to come together, each of them sharing their electrons? That would take me through this transition state, and it would give me a new product, which is called ethane. So that's B plus B. So the termination steps kill the radicals. But in order for this to happen, in solution, two radicals would have to be close together. So these steps aren't necessarily, like if you'd say, well, what produces more product, the propagation step or the termination step? By far and away the propagation step, because statistically, when you have a BR dot, it's likely to run into an intact methane molecule than it is to find a methyl radical, because the methyl radical is trying to react with something else. So just statistically, you're going to have more product in the propagation steps. And this last step is what's called coupling. So when two alkyl radicals come together, that's a coupling step. We talked briefly about the side reaction in a Grignard called Wirtz coupling. The fact that it's called Wirtz coupling means that that mechanism is probably a free radical one. So there's our 6 steps in the mechanism with the transition states. So when I give you a problem like this and ask you to write the mechanism, and I will, either as a take-home quiz or as a, well, it'll be a take-home quiz first. I have to tell you what hydrogen I want you to replace. But once I do that, then you basically go through each one of these steps. We have the advantage of we've already written at least one transition state in the past. Right, so this is the free radical mechanism. So those are the 6 steps. All right, everybody okay with that? So let's go on to more exciting stuff. Let's start with something simple like pentane or propane. Because now we need to talk about, well, let's make it more complicated than methane. And we'll make it a little bit more complicated by using propane. How many different products could we get from doing a free radical halogenation on propane? How many products would I expect? Katie? 2? Was it 2 or not? You have to be confident and bold, even if you're wrong. And you're not. So you can be 2. Do we all agree with that? We should, since I just said it was right. Is that a bird or is it a little kid? Let's substitute a hydrogen for a halogen. This is how we'll know. There's one product, 1 bromopropane. I should probably put in the CH3s and the CH2 and the CH3. Okay, so here is one of the possible products, 1-bromopropane. How many hydrogens could I replace with a bromine and get 1-bromopropane as the product?
6.
See, there's a confident answer. You're expecting me to say it's wrong, right? No, it's right. 6. All 3 of these, and then all 3 of those. So there are 6 hydrogens that give you 1-bromopropane. So what I'm going to do is I'm going to label the different hydrogens that give me product A. So if this is product A, those 2 CH3s I'm going to call A, because each one of those is going to give me that product. That means I have how many products left over? Or how many, I only have one, well, I'll just say it. I only have one product left, right? And that is 2-bromopropane, which I will call product B because it comes from either of those 2 hydrogens being substituted with a bromine. So for propane, there's 2 possible products. 1-bromopropane and 2-bromopropane. There are 6 hydrogens that would give me 1-bromopropane, and there are how many hydrogens that give me 2-bromopropane? 2. There's 2 H's. Will the 6 H's and the 2 H's come into play? Yes. Now, I have to go back and say, at least from people that are in my lab, that if I would have given you propane and said, how many unique hydrogen peaks should you see in propane? You would hopefully say 2. And one of the ways to get that number 2 is to substitute a bromine or a chlorine for every hydrogen and see if you make a new product. That's the way you can determine the number of unique protons in an NMR spectrum and predict. So when we talked about that, that's kind of the method we used. It's more helpful when we'd already had it, well, I guess, a semester earlier. But we're doing the same thing here. So the first thing whenever we're doing this reaction is that we have to figure out how many different products can I make. So in this reaction, I can make 2. Anybody psychic enough to figure out what my next question is going to be? Take a shot.
What's the major product?
What's the major product? You really have to be all that psychic. So what's the major product? Oh, okay. Go ahead and take a shot.
A.
Why A? I'm curious.
It's more likely to, it's 3 times more likely to react to the hydrogen on the end than in the middle, which is 3 times the size.
Right, so you can use the ratio of the hydrogens to predict that. I was going to ask that question rhetorically, which means I was going to answer it. And my answer would be, and you're correct, but my answer would be, what's the major product of that reaction? It depends. It actually depends. So the logic of more hydrogens giving the product is a correct one. But then let me also counteract that by saying, what kind of radical did I make product B from? Primary, secondary, or tertiary? It came from a secondary radical. This came from a secondary radical. What kind of radical did product A come from? A primary radical. Now, we have the advantage of basically knowing that which radical is more stable. Secondary. Because they follow the same rules as a carbocation. The big difference being that you're not outlawed from writing a primary radical. Primary radicals, because there's 7 electrons, it's close enough to 8 that primary radicals exist at room temperature. Whereas primary carbocations are still forbidden in this class. And I had to write numerous times, oh no, a primary carbocation. And then no, with at least 1 to 3 exclamation points. So we're allowed to write primary radicals. We're not allowed yet, well, we're only allowed to write primary carbocations in lab, in mass spectrometry, because we get that high energy environment. So I would counteract that by saying, but wait, how many reactions have we done where the major product has come from the more stable intermediate? If I don't want to count them all, the answer would be more than 1. Right? So when I say it depends, which one of those 2 factors is playing the most important role? Is it statistics, the 3-to-1 advantage that product A has? Or is it the stability of the radical, which is the advantage that product B has? Again, a rhetorical question. Although you could jump in, I'm always interested in hearing thoughts. Oh, okay.
Depends on the environment you put it in. It's a high energy environment, it'll probably take statistics.
That's actually true. That is. Somebody asked the question about what's the difference between light and heat. That's the difference. So we're going to actually find out that if we do apply heat to the reaction, we do it in a high temperature environment, we are going to get the statistics. And if we do it at a low temperature environment like light at room temperature, we're going to favor the secondary product, the most stable intermediate. But it's actually, there's going to be a formula that we should use, Jacob.
Then dependent on the light, because earlier I said with that
Right.
UV light, if we were to use UV light, would that cause statistics to be bigger because it'd be higher energy?
Typically, we have to use a high energy environment. We have to use a high temperature. So, last thing, because I got to hand out your exams, because I said we're going to revisit Hammond's postulate, and we're going to revisit the Arrhenius equation. And so between those two, that's going to allow us to make the link. So it's actually a temperature phenomenon. I'm going to go back and I'm going to use my bird analogy. You know, supersonic birds that fly over every height mountain, and birds near death that can only go over the mountains or else they crash into them and die. I'm going to do that on Friday. So we'll talk about the explicit reasons for this. But again, we have the advantage of having talked about the Hammond's postulate once before, and if not, we'll talk about it again. Okay, so you can go ahead and I'll hand out the exams by the door, and you can put your homework problems over on one of the tables over here. We'll stay there, Bishop.
Sydney, Lexi, Kristen, Patrick. Ben, Shelby. Haley. Michael. Joe. Carolyn.
I didn't.
Aisha.
I thought people were going back here.
Taylor, Katie, Lucy,